he just missed that whole explanation. Anthony, hi. Okay. All right. So let's do this. Suppose we roll a ball up a ramp. Okay. And it goes up to some height before coming back down. Okay. So. And then I suppose, shoot, this is, half the battle is coming up with good wording on these problems. That's sort of what I'm struggling with here. All right, so Roy rolls a ball up a ramp to height h. Cool? So it's one of those, it's worded terribly, but you know what I mean, like ball goes up the ramp and it comes back down. Cool? All right. Let me write it this way instead of saying how much higher. How many times higher will it go if he rolls it, I don't know, 4 times as fast? All right, so this is what I did a rotten job of wording on the test. Okay, so what are the two things that we're relating here? How high the ball goes is being related to the velocity, the initial velocity that we roll it at, right? Okay, so we need to pick an equation that has those things in it. Stupid smart board. I'm going to start calling it a dumb board. Okay, so we need to find an equation that relates. What should I use instead of h, you guys? What are we really talking about here? Delta x, right? So I need to find an equation that relates displacement to initial velocity. So let's make a list of equations that have those variables in them. Okay? Now eventually you'll get the hang of doing this. You don't have to make a big list. But all right, so I'm just going to brainstorm. Let's see. This is an equation. Does that equation help me any? Yeah, the time is not going to be the same in both circumstances, right? If I roll it faster, then the time it takes to go up and down is going to be different. So this equation's no good because this is a third variable that is changing. Okay? So I need to pick one equation where the only two things changing are displacement and VI. All right, so this one. Same problem. All right? Oops. Let's see. Is my acceleration going to change if I roll it faster? No, because the acceleration is determined by the ramp. Final velocity, isn't that going to change? No, because it's going to be 0 at its highest point. So this is the equation I want to look at, right? Cool? So let's see. Let's solve for displacement. I'm so mad at this smartboard right now. View, dual page on. There we go. All right, so let's solve this equation for displacement. So displacement is, displacement is, I gotta calibrate my board, VF squared minus VI squared all over 2A, right? Now, can I simplify anything?
Yes.
VF is 0. Oh, right on. Displacement is negative VI squared over 2A. Oh, so if I multiply my velocity by 4, how is that going to affect my displacement?
16.
Y times 16. Because it's squared. Right? So anything right? You guys agree that the 4 is going to get squared? And I'm going to end up getting 16 times this mess, right?
But that's the same mess.
Say it again, sorry.
It's like the same
But
mess.
it's the same mess that we originally had.
So then you just have it at 16, so then you have 16.
Exactly. Does this make sense, you guys?
A lot.
Okay. I'm sorry it took me so long to get there. Again, with this just being my second time teaching this, it's going to take me a little while to figure out some of these ways to explain stuff. Do you know what I mean? Because, like, to me, this is, like, intuition. And I don't mean that in a snarky way, but just, like, I've done more math than you guys have. So it just took me a little while to figure out how to explain it to you guys. Adam. Close. Is it going to go higher or less high if I roll it faster? So 16H. Yeah, so then, yeah, so your answer then would be 16H. Daniel.
Yeah, this is gonna be a little weird, but say we had like a question pretty much exactly like this on test or like what we had on the guide page, and instead of just like doing the math like this regularly, we wanted to say like, so the way I looked at it when I redid it on Friday was that since it's got initial velocity, acceleration is constant, and the time is to the top is when it takes the velocity to reach 0, I said that the time is proportional to the velocity, and then your displacement is proportional to both time and initial velocity. So that's why you square it.
Yep. If that makes sense to you, awesome.
I could just write that.
Yep.
6.
So, you don't need to show a ton of work for these, you guys. Like, honestly, for this, I kind of feel like if you wrote down this equation and then just wrote down 16H, that's fine. Like, there's not a lot to show. Do you know what I mean? Yeah, right? Do you know what I mean? Margaret.
Okay, so on the test, I did exactly this. I just, I left it like with the, you see how like the mess is, like with the,
This?
say 16? Yeah, but like, instead of saying like 16H, I had the other one.
You had 16 times this.
Yes.
I know a lot of people did that, and that was because I did a
Okay.
bad job of wording the problem.
Okay, but like
Censored
in
myself.
general, if you did do that, say on an AP test, because you like messed up.
The test, the AP test will be worded clearly. It'll say how many times higher
Okay.
instead of the mess that I had on the test.
But theoretically, would have been full credit.
It would depend on how the problem was worded.
So if it wasn't
The way that it was, I had it worded, yeah, technically you should have gotten full credit.
Oh,
But I'll tell you this, you guys, these are going to be the multiple choice questions.
no.
Let me say that again. These are going to be the multiple choice questions. You have 35 of these to do in 45 minutes. Okay? So, you need to know how to do them. Alright? So we'll keep practicing them all year. I'll do another one right now. Okay? Or better yet, I'll give you guys one to try. Okay? And we'll be going through them all year. But anytime you get these problems like this, where it's like no numbers and you're looking for relationships, that's going to be our go-to phrase, our mantra, if you will, which is this. What are A and B? What are the two things we're trying to find out the relationship between? And what equation can I use that relates those two things and only those two things? Make sense? And does everybody understand why I had to eliminate these top two choices? Because the time is also changing. Follow? All right, let's try another one. Acceleration of gravity on Earth is about negative 10 meters per second squared. Acceleration of gravity on Jupiter is about negative 50 meters per second squared. Don't quote me on that. I actually think it's closer to 25, but whatever. We're going to pretend. All right? Here, do this. On planet X, that's where Marvin the Martian lives. All right? How many? So assuming that you can throw something just as fast on planet X as you can on Earth, how many times higher can you throw something on planet Earth? I'm going to stick with the wording. It's bad wording. But how many times higher can you throw something on planet X than you can on Earth? So, see if you can figure it out. And it's not actually higher, right? It's going to be less high. So on Earth, you can throw it to a height of h. On planet X, you can throw it to a height of something times h. That's what I'm looking for. Yeah.
Yeah, it accelerates just like it's right on. Wouldn't it be weird if it's how like it'd be terrifying if you made like this.
All right. Do we need another minute? See a couple people still writing. I'll give them another moment. All right, I'm going to pick on somebody in a minute, so make sure you're kind of following along and ask somebody for an equation, somebody who may or may not have their hand up. Yeah, so again, the question is, assuming you can throw the ball at the same speed, if on Earth it goes to a height of h, then on planet X it will go to a height of something times h. Find the something. Question, Patrick, or answer? Okay, give me a minute. Patrick, no offense, but I think, seeing as you were the one person who got everything on that last page right, I think you're the one person that's not going to call. So good job, good job. All right. Sorry for writing you up. Patrick, though, is this easier than what you were doing when you did it? Or no?
Yeah, it's easier. Like, I plug this in.
Okay, yeah.
It's like arbitrary numbers.
Right, I got you. Okay, so Molly, pick an equation.
Oh, yes.
What do you got?
2a delta x
2a delta x equals vf squared minus vi squared. So which of these two variables are we relating? Right, so the gravity is our acceleration and the height is our displacement, right? Okay, but our VF and our VI are staying the same, right? Okay, so we want to solve for delta x, right? So delta x is VF squared minus VI squared all over 2a. So on planet X, we've got 5 times the acceleration. How's that going to affect our displacement? 1/5. So 1/5 height is your answer. Make sense?
Yes.
All right. Follow-up question. If on Earth it's in the air for a time of t, how much time is it in the air for on planet X? So now we're dealing with time. So pick an appropriate equation and solidify it. Yeah, solidify what?
This is so much easier than I think the other way
Yeah.
I was interpreting.
Yep. So I'm sorry that I made this such a mess. Again, learning curve for me as well as you guys.
That means, like, if everyone got last stage, then I wouldn't have gotten a good grade on this one because it was
Gotcha. All right, so real quick while you guys are thinking, here's the deal for the retake. You've got 3 options. You can retake just the last page, everything but the last page, or the whole thing. Okay? Cool? So, I'm guessing most of you will be either just last page or whole thing, and we might have one exception. Okay. And if you do not want to retake it, that's okay too. You'll just use the time to work on the chapter 3 homework, which is due Thursday. Okay? Cool? Alright, so, Jacob, how are you doing over there?
I'm good.
Doing okay? Were you following along here or no?
It makes sense.
Okay, so what equation, so the question was, how is the time going to be affected? So what equation are you looking at? Yeah.
So, VF equals VI plus AT.
VF equals VI plus AT. Let's see. Our VF and VI are not changing. The acceleration changed, and I want to find out how that affected the time, right? So I should rearrange this and solve for t. VF and VI are staying the same, whether I'm on Earth or on planet X. Right? Because you're throwing it at the same speed, it's going to stop at the top, and then come back down to the same velocity. So 5 times the acceleration would give you 1/5 of the time. Good? Yes, and then yes. I don't know how that would help you here. To find time?
Oh, wait.
Yeah. But yes, if you want to use that to find the height, sure. I think you're making it harder than you need to, but that does work. Because it's 1/2 mv squared, right? It's that v squared. Yeah. Okay, cool. Adam, didn't you have a question too? Oh, I got you. Are you good? All right. Are we good, you guys? Okay. All right. Excellent. Yes.
Would it work with a 2a delta x equation?
No, because that doesn't have time in it. Follow? Everybody good? All right. Now, if you're right there, if you're sitting there now going, I still don't know how to do this. I'm around before school in the morning. We have a staff meeting after school that gets out at 4:15, so I'm available from 4:15 till later. Honestly, I'm just going to kind of camp out here tonight. I got a ton of stuff I got to get caught up. So I'll be here late. Okay. So yeah, so I'll be here. All right. All right. Good. Better than we were.
Yeah.
All right. High five whoever's next to you. If no one's next to you, high five yourself. All right. No. Okay. All right. So let's finish up our discussion of chapter 3 and see if we have time to get into chapter 4. All right. So chapter 3 is just vectors. Chapter 3 is just vectors. Okay, adding and subtracting vectors, basically. All right, really, I think the only thing that we learned new yesterday was the unit vector notation thing, right? Which is just a handy way to keep track of your x and y components, right? The I goes with your x component, the j goes with your y component. Other than that, it's business as usual, right? Okay, so adding the vectors is easy, right? That's what we did last year, right? You add up all your i's, you add up all your j's, i.e. add up all your x's, add up all your y's, right? Are we all good with that? Yeah. All right, so I want to do one quick example with subtraction. I will say that this example is tougher than what you guys will get on the homework because it assumes some knowledge about forces, which you should know theoretically, but it's been a year. You may have forgotten stuff over the summer. All right. So know that this is harder than what you'll get on the homework. But it has built into it a vector subtraction problem. Follow? Okay, so here we go. It says Roy uses a force of 500 newtons at 30 degrees below the horizontal to push an 80-kilogram box across the floor. The box experiences an acceleration of, notice the notation there, 3i meters per second squared. What's the I telling you? It's going horizontal, right? Okay? Calculate the coefficient of friction between the box and the floor. Okay? So this is sneakily a vector addition or vector subtraction specifically problem. Where do you think we should start?
Picture.
Draw a picture. Great. All right, so here's the box, right? So let's start by making our three-body diagram. So the first thing we've got to deal with is the force of Roy, right? So the force of Roy is 500 newtons at 30 degrees below the horizontal, right? What do I need to do with it? Draw it. Well, okay, sure, yeah. There we go. 500 newtons, force of Roy. 30 degrees is here, right? Now what?
How do you know it's not on the other side?
It's not negative.
What do you mean? Like over here?
No,
Never mind.
Are you sure? Everybody good with why I put the angle there? Okay, so draw on your triangle. Remember, your components have to be head to tail. So here's the force of Roy in the x direction, force of Roy in the y direction. Do your trig. This one ends up being negative 250 newtons. This one ends up being 500 times the cosine of 30, 433. Good. Make sure your calculator's in degrees. So I'm going to rewrite my force of Roy. It's now 433I minus 250J newtons, N for newtons. Cool? All right, now let's make our free body diagram. So over here, let's see. Here's my force of Roy in the x direction. It's, nope, that's not the x direction at all. Force of Roy in the y direction is negative 250 newtons. We've got an 80 kilogram box. So what should I do that I haven't done yet? Force of gravity, right? Which I'm going to draw in a different color just because I'm... So force of gravity is 80 times 9.8, which is negative 784, I think. You're afraid of me?
in small legs.
Scary math in your head.
Oh, gotcha. Yeah. I have a lot of the multiples of 9.8 memorized just because they come up all the time. Force of Roy in the x direction is 433 newtons. All right. So is everybody okay with that?
Yes.
So we have three known forces. Specifically, the force of Roy in the x direction, force of Roy in the y direction, force of gravity, and two unknown forces, right? What are the two unknown forces? Friction and normal force. Here's my normal force. Here's my force of friction. All right, now, I know you guys know how to find the normal force using methods I showed you last year. Okay, and I know I'm going to go through this a slightly different way than we did it last year because it illustrates the idea of vector subtraction. Cool?
Yeah.
All right, so are there any questions so far? Okay, now, the one other thing that I know is I know my acceleration. It's a forces problem. I gave you the acceleration. What should you do?
Find the net force.
Find the net force. Net force is mass times acceleration. So that's a thing, you guys. I know we're not forces yet, but I'm just reintroducing you to the stuff we talked about last year. If you know the mass and the acceleration, holy beans, find your net force. Okay, Margaret. I'm sorry? Oh, yeah, just grab a pass. Okay, so our net force is mass times acceleration. So 80 kilograms times, watch how I'm going to write this. What's my acceleration? 3I meters per second squared. So I'm going to get 240 I newtons. Follow? Problems? So I'm going to write that over here. Net force is 240 I newtons. I'm sorry.
Because I interrupted you.
Okay, don't worry about it. It takes 2 seconds. Okay. All right. Yes.
What the heck is that?
Did I lose you? Where did I lose you?
Three IU. Okay, I'm there now. I'm back.
You good? Where did I lose you? Because if I lost you, I'm sure there were some other people that lost.
No, I neglected to observe that 3 IU second squared was the gravity, or was the acceleration.
It's the acceleration of the object, right?
Object.
Everybody good?
Yes.
All right, great. So, what does all this have to do with vector addition and vector subtraction? Well, look. Oh, shoot, that's not what I wanted to do. Look, our net force is, well, let's see, name the forces. There's the force of Roy, the force of gravity, the force of friction, and the normal force, right? Good? All right, so I'm going to write this out vertically now, I guess. All right, so let's rewrite it this way. It's force of Roy plus force of gravity plus force of friction plus normal force has to all add up to net force, right? So last year I had you guys doing charts, x components, y components, right? Follow or no? Everybody good? Sarah, you okay over there?
Yeah, I have no idea what you're talking about, though.
With the charts? Okay, maybe Mr. Hernandez didn't use the charts.
No.
No? Okay. All right. You'll be okay. Bear with me for a minute, and I think you'll be okay. All right. So, the force of Roy. We know this. The force of Roy was... I'm going to skip units. Everything here is newtons, right? So let's not worry about units. So the force of Roy is 433I minus 250J, right?
Yeah.
Okay, in vector unit notation, I would like one human being in this classroom to please describe for me the force of gravity. What do you got, Adam Fox?
0I minus 784 J.
Right? Why 0I? Because gravity doesn't pull sideways, it pulls down. All right? Now, force of friction. Everybody point for me. Which way is friction going? That way, right? So, let's call this force of friction in the x direction, I.
Wait a minute.
Right? Plus 0J. Everybody good? Now I need somebody to describe for me the normal force in vector component form. What's the x component, you guys? 0I plus the normal force vertically in the j direction. What's the... Oh, yeah. Oh, it does. All right. All right. It's got to equal my net force. So what's my net force, you guys? 240I plus 0J.
That's if you edit. Oh.
Now, do you have to write in all the zeros? No. I'm doing it to be thorough. We found it before. Remember, it was 80 times 3. Peter, you good?
Yeah.
You sure?
Just, I'm free.
All right, so those of you who are in my class, do you see that this is the same as the chart?
Yeah.
All right, now, Hernandez, Pete, stop to me for a minute. Does this make sense? You guys have never seen the charts. Does doing it in vector notation make sense? Unit vector notation?
Way more.
Okay, so check it out. So now what do? We need to find our force of friction and our normal force. Look, all of these have to add up to that. Right? So, cool. All right, so this gives me this equation. 433 plus 0 plus the force of friction in the x direction plus 0 has got to equal 240. Oh, let's see. Let's subtract 443, and our force of friction in the x direction is...
Negative 193.
Thank you, negative 193. Oh, hooray! Follow? Yeah, I'm being... Oh, right. Well, no, x. That's telling me in the x direction. So I could do this. Right?
Do you have to write 0 here?
No, you do not need to write... If one of your components is 0, you don't have to write the zeros. You guys don't need to apologize when you're coming up to get a pass. Just do it. All right. Everybody follow? All right, now we can do the same thing over here. So let's see, negative 250 minus 784 plus 0 plus the force normal in the y direction has got to equal 0. So the force normal in the y direction is 1034. Follow? Yes.
So can we not do this, or do you not want us to do this just by like writing it out and like adding negative 250 and negative 784, like reading it out?
I don't care.
Oh,
As long as you understand what's going on, doesn't matter to me. All right, does this all make sense? All right, now eventually we'll get to the point. I mean, like if what we did in honors works, cool. But this is, in terms of vector addition and subtraction, how you do it. Cool? So why am I referring to this as vector subtraction? Isn't this, so this is basically number plus x equals number. How do you solve? If you have number plus x equals number, how do you solve for x? You subtract, right? Okay, so in algebra they teach you to write subtraction as adding a negative. That's basically what we're doing here. Follow? All right. Okay, so now we have one last step, right? We just need to find our coefficient of friction. Wasn't that the original problem? So force of friction, I'm being a little sloppy here, is coefficient of friction times normal force, right? What kind of friction are we talking about here, you guys? Very good. This was all kinetic. Nice. Nice. You nailed it. You were right on top of it. All right. So that means our coefficient is force of friction over normal force. Here, we're just talking about magnitude. When you use this equation, this is a reference to the magnitude of the vectors. So you don't need to worry about your i's and j's. So our friction was 193. Our normal force was 1,034. Divided out, and it gives you 0.187. Let's just call it 190. All right. Does this make sense?
Yeah.
Vector subtraction. All right. Now, the last thing I want to talk about real quick is graphically. Okay? So, if I tell you vector A looks like this, and vector B looks like, I don't know, maybe this, then what does A plus B look like? So, to add vectors, how do we do it? We place them head to tail, right? So here's my vector A.
Look at this. Honestly. Nobody uses their smart board.
yeah, obviously, like
Here's my vector B. Here's my A plus B, right? Does that make sense? All right, now. How do I do A minus B? You got an idea, Patrick? Flip what around? Which vector? B. This is the exact same thing as A plus negative B. So what? Everybody point in the direction of vector B for me with your hand. Vector B goes this way. What direction? All right, so B goes this way. What direction does negative B go? Just flip the direction around, right? So here's A.
That's weird.
Ah! All right, so there's my vector A.
He's not of this world.
Here's my vector B, right? Is that right? No, what do I need to do? Flip it around. So I'm going to cheat. It's the best I got, sorry. Did that make sense or no? Maggie, what's wrong? Are you lying? Alright, so is everybody good with what I just did here? Alright, and here then is A minus B. Make sense?
Yes.
Cool? Make sense? Any questions? All right, here's another way you could do the same problem. Oh. So here's another way you could do the same problem, and sometimes I find this is a useful trick. So suppose I've got A minus B. Let's give that a name. Let's call it C. Okay? Isn't this the same as A equals? Do I want to write C plus B or B plus C? I think I want to write B plus C. So how does that help me? All right, well, look. Look. So here's my vector B, right? So there's my vector B plus some vector C. So here you got to think for a minute. So when I add vector C, I don't know what vector C is, but when I add vector C, it's going to kind of go, I don't know, like this somewhere, right? I just don't know what direction vector C goes in, right? But once I have my vector C drawn in, that's got to equal A, right? How will I draw A? How do I draw A, you guys?
No, you could have a strike if everyone goes up with one every
Well, so if, hypothetically, suppose this crappy arrow right here is the answer to C. So if A is B plus C, then wouldn't A be this line here? Right? So my resultant vector has to start here, right? Oh, but I know what my resultant vector is. So let's see. My resultant vector, oh, why would you do that to me?
like the Windows X.
Okay, look, I know what my resultant is because I know what vector A is. Vector A was this one, right? Right? So now the question is, vector B plus what vector C equals A? Don't you guys agree this is B plus C equals A, right? And look, this looks the same as this one, right? Yay, vectors! Alright. So, you need to be comfortable manipulating vectors. This illustrates the fact that the order in which I add vectors A and B doesn't matter, right? Cool? Yes. You sure? I said A and B. I meant to say B and C, but whatever. You sure?
Yeah.
All right. Any other questions here, you guys? All right. When does the bell ring today? 45, is that right?
Yes.
Okay. All right. So right now you guys know everything you need to know to do the Chapter 3 homework assignment. It's due Thursday. All right? Let me stop recording real quick.
Hi, Anthony. Bye, Anthony.
Hi, Anthony. Bye, Anthony.